Welcome, fellow travelers of the cosmos, to a deep dive into the eerie, mind-bending world of quantum mechanics. This is a realm where the very fabric of reality seems to twist and turn in ways that defy our everyday experiences. It's a place where particles can exist in multiple states at once, where the act of observing something can change its very nature, and where connections can be made across vast distances instantaneously. It's a world that challenges our understanding of the universe and forces us to rethink what we know about the nature of reality itself. You know, the realm where the universe throws out the rule book of classical physics. In this strange and fascinating domain, the laws that govern the macroscopic world we are familiar with no longer apply. Instead, we encounter phenomena that seem to belong to the realm of science fiction. Imagine a place where particles can be in two places at once, where they can communicate with each other instantaneously, and where the very act of measurement can alter the outcome of an experiment. This is the quantum realm, a place that defies our intuition and challenges our understanding of the natural world, and replaces it with something altogether stranger. Something that even Einstein himself struggled to fully embrace. Despite his groundbreaking contributions to the field of physics, Einstein was famously skeptical of some of the more bizarre implications of quantum mechanics. He once remarked, "God does not play dice with the universe," expressing his discomfort with the idea of randomness and uncertainty at the heart of quantum theory. Yet, despite his reservations, the evidence for quantum mechanics continued to mount, and today it stands as one of the most successful and well-tested theories in all of science. We like to think we've got the universe figured out. For centuries, humanity has gazed up at the stars and sought to understand the cosmos. We've developed sophisticated theories and models to explain the motions of planets, the behavior of light, and the fundamental forces that govern the universe. We've built telescopes to peer into the depths of space and particle accelerators to probe the smallest building blocks of matter, and yet, despite all our progress, the quantum realm remains a place of mystery and wonder, a domain where our classical intuitions are turned on their head. Planets orbit stars, apples fall from trees, cause and effect. These are the familiar patterns and regularities that we observe in the macroscopic world. They are the foundation of classical physics, the set of rules that describe the behavior of objects on a human scale. But when we delve into the microscopic world of atoms and subatomic particles, we find that these rules no longer apply. Instead, we encounter a world of probabilities and uncertainties, where particles can exist in multiple states at once, and where the act of observation can change the outcome of an experiment. But at the subatomic level, the universe dances to a different tune, one composed of probabilities, uncertainties, and interconnectedness that seems almost magical. In this realm, particles can exist in a superposition of states, meaning they can be in multiple places or have multiple properties at the same time. This is a fundamental aspect of quantum mechanics, and it leads to some truly mind-bending phenomena. For example, the famous double-slit experiment demonstrates that particles can behave like both particles and waves, depending on how they are observed. This duality is at the heart of quantum mechanics and challenges our classical notions of reality. It's a reality that challenges our very notions of what it means to exist, to observe, and to know. In the quantum realm, the act of observation plays a crucial role in determining the outcome of an experiment. This is known as the observer effect, and it suggests that the very act of measuring a quantum system can change its state. This has profound implications for our understanding of reality, as it implies that the universe is not a fixed, objective entity, but rather a dynamic and interconnected web of possibilities. It forces us to reconsider our notions of causality, determinism, and the nature of existence itself. Today we're going on a journey to explore 5 mind-blowing aspects of quantum mechanics that will leave you questioning everything you thought you knew about the universe. We'll delve into the mysteries of superposition, entanglement, the observer effect, quantum tunneling, and the many worlds interpretation. Each of these concepts challenges our classical intuitions and offers a glimpse into the strange and fascinating world of quantum mechanics. By the end of this journey, you'll have a deeper appreciation for the complexity and beauty of the quantum realm, and you'll be left with more questions than answers. We'll delve into the heart of atoms, where particles can be in multiple states at once. This phenomenon, known as superposition, is one of the most fundamental aspects of quantum mechanics. It allows particles to exist in a combination of states, and it is the basis for many of the strange and counterintuitive phenomena we observe in the quantum realm. For example, in the famous Schrödinger's cat thought experiment, a cat is placed in a box with a quantum system that can be in one of two states. Until the box is opened and the system is observed, the cat is considered to be both alive and dead at the same time, illustrating the concept of superposition, where the act of observation shapes reality. This is the observer effect, and it suggests that the very act of measuring a quantum system can change its state. This has profound implications for our understanding of reality, as it implies that the universe is not a fixed, objective entity, but rather a dynamic and interconnected web of possibilities. It forces us to reconsider our notions of causality, determinism, and the nature of existence itself. The observer effect is a key aspect of many quantum experiments, and it highlights the importance of the role of the observer in the quantum realm, and where seemingly impossible connections defy the limits of space and time. This is the phenomenon of quantum entanglement, where particles become interconnected in such a way that the state of one particle is dependent on the state of another, no matter how far apart they are. This means that a change in the state of one particle can instantaneously affect the state of another particle, even if they are separated by vast distances. This phenomenon has been experimentally verified and has profound implications for our understanding of the nature of reality and the interconnectedness of the universe. So, buckle up, engage those curiosity engines, and prepare to have your mind blown wide open as we unlock the secrets of the quantum realm. This journey will take us to the very edge of our understanding, where the boundaries between science and philosophy blur and where the mysteries of the universe are revealed in all their strange and wondrous glory. Whether you're a seasoned physicist or a curious layperson, there's something here for everyone. So sit back, relax, and get ready to explore the fascinating world of quantum mechanics. Let's dive in and see what we can discover together. In the comfortable, predictable world of classical physics, we're used to a certain level of certainty. The laws of motion, as laid out by Sir Isaac Newton, have given us a framework to understand and predict the behavior of objects in our everyday world. From the simple act of an apple falling from a tree to the complex orbits of planets around the sun, classical physics has provided us with a sense of order and predictability. We can predict the trajectory of a baseball with remarkable accuracy. When a pitcher throws a ball, we can calculate its path, speed, and where it will land. This predictability is comforting. It gives us a sense of control over our environment. Similarly, the phases of the moon follow a predictable cycle. We know when the moon will be full, when it will wane, and when it will wax. This regularity has guided human activities for millennia, from agriculture to navigation. The ebb and flow of the tides are another example of this predictability. Governed by the gravitational pull of the moon and the sun, tides rise and fall with a rhythm that can be charted and anticipated. Fishermen, sailors, and coastal dwellers have relied on this knowledge for centuries. But venture into the quantum realm, and you'll find that certainty goes out the window, replaced by a world painted in shades of probability. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, introduces a level of unpredictability that challenges our classical intuitions. This is the essence of Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. Formulated by Werner Heisenberg in 1927, this principle states that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle, such as its position and momentum. This principle, my friends, isn't just a statement about the limits of our measuring instruments, it's a fundamental truth about the nature of reality itself. It tells us that the very act of measuring one property of a particle with high precision inevitably disturbs another property, making it less precise. It tells us that we can't simultaneously know both the position and momentum of a particle with absolute precision. The more accurately we try to measure one, the less accurately we can know the other. This isn't a flaw in our technology, it's a fundamental characteristic of the quantum world. Imagine trying to pinpoint the location and speed of a buzzing electron. Electrons, which are subatomic particles, don't behave like tiny billiard balls. Instead, they exhibit both particle-like and wave-like properties. This duality adds to the complexity and uncertainty of their behavior. The more accurately you measure its position, the fuzzier its momentum becomes, and vice versa. This trade-off is not just a quirk of measurement, it's a reflection of the intrinsic nature of particles at the quantum level. It's as if the universe itself is playing a game of hide and seek with us. It's like trying to nail jelly to a wall, a frustrating yet profound exercise in futility. This analogy captures the elusive and slippery nature of quantum particles. No matter how hard we try, we can't pin down all their properties at once. This inherent uncertainty isn't due to some technological limitation we can overcome. It's not a matter of building better instruments or refining our techniques. Instead, it's a fundamental aspect of the quantum world, woven into the very fabric of reality. It's baked into the fabric of the universe, a cosmic game of chance playing out at the smallest scales. This randomness is not just a feature of the quantum world, it has profound implications for our understanding of the cosmos as a whole. And as we'll see, this uncertainty has profound implications for our understanding of the cosmos. It challenges our classical notions of determinism and forces us to rethink the very nature of reality. The quantum world is a place where particles can exist in multiple states at once, where they can be entangled across vast distances, and where the act of observation can influence the outcome of an experiment. Take, for example, Schrödinger's cat, a famous thought experiment proposed by physicist Erwin Schrödinger. In this scenario, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of both alive and dead states. This thought experiment illustrates the bizarre and counterintuitive nature of the quantum world. It forces us to confront the idea that reality, at its most fundamental level, is not as straightforward as it seems. The act of observation plays a crucial role in determining the state of a quantum system. Another mind-bending phenomenon in the quantum realm is entanglement. When two particles become entangled, their properties become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, defies our classical understanding of space and time. Entanglement has been experimentally verified and is now a cornerstone of quantum mechanics. It has practical applications in emerging technologies such as quantum computing and quantum cryptography. These technologies promise to revolutionize fields ranging from information security to materials science. Quantum computers, for instance, leverage the principles of superposition and entanglement to perform calculations that would be impossible for classical computers. They have the potential to solve complex problems in seconds that would take classical computers millions of years to crack. Quantum cryptography, on the other hand, uses the principles of quantum mechanics to create unbreakable codes. By exploiting the behavior of particles at the quantum level, we can achieve levels of security that are theoretically immune to hacking. These advancements are just the tip of the iceberg. The quantum revolution is still in its early stages, and we are only beginning to scratch the surface of what is possible. As we continue to explore the quantum realm, we will undoubtedly uncover new phenomena and develop new technologies that will reshape our world. But with these advancements come new challenges and questions. The inherent uncertainty of the quantum world forces us to rethink our understanding of reality. It challenges our classical notions of cause and effect, and it raises profound philosophical questions about the nature of existence. As we delve deeper into the quantum realm, we must grapple with these questions and seek to understand the true nature of the universe. The journey is as much philosophical as it is scientific, and it requires us to expand our minds and embrace the unknown. The end of certainty in the quantum world is not a cause for despair, but rather an invitation to explore new frontiers. It reminds us that the universe is far more complex and mysterious than we ever imagined. And in this complexity, we find beauty, wonder, and endless possibilities. So as we continue our journey into the quantum realm, let us embrace the uncertainty and the challenges it brings. Let us remain curious and open-minded, for it is through this spirit of exploration that we will uncover the secrets of the universe and expand the horizons of human knowledge. The end of certainty marks the beginning of a new era in science, one where we must learn to navigate the unpredictable and the unknown. It is a journey that will test our ingenuity, our perseverance, and our willingness to question everything we thought we knew. But it is also a journey filled with promise and potential. The discoveries we make in the quantum realm will not only deepen our understanding of the universe, but also pave the way for new technologies and innovations that will transform our world. So let us embrace the end of certainty and embark on this exciting journey into the unknown. The quantum world awaits, with all its mysteries and wonders ready to reveal its secrets to those who dare to explore. Hold on to your hats, folks, because things are about to get really weird. We're about to dive into a world where the rules of classical physics no longer apply. We're diving into one of the most mind-boggling aspects of quantum mechanics' wave-particle duality. This concept challenges our very understanding of reality. This is the seemingly paradoxical idea that particles, like electrons and photons, can behave like both waves and particles depending on how we choose to observe them. It's a fundamental principle that has puzzled scientists for decades. The classic experiment that demonstrates this mind-bending phenomenon is the double-slit experiment. This experiment has been a cornerstone in the study of quantum mechanics. Imagine shining a beam of light at a barrier with two narrow slits cut into it. This simple setup reveals profound truths about the nature of light and matter. Behind the barrier, there's a screen that records where the light hits. This screen captures the resulting pattern, providing crucial data for analysis. Now, if light were purely a wave, we'd expect to see an interference pattern on the screen with bright and dark bands where the waves from the two slits interfere constructively and destructively. This pattern is a hallmark of wave behavior, and that's exactly what we see. The interference pattern confirms the wave nature of light. But here's where things get really strange. The plot thickens as we delve deeper. If we send individual particles, like electrons, through the slits one at a time, we still observe an interference pattern building up over time, even though each electron should only go through one slit or the other. This defies our classical intuition. It's as if the electron is interfering with itself. This self-interference is a key feature of quantum mechanics, revealing the dual nature of particles. Welcome back, cosmic explorers. Today we embark on a journey that will stretch the limits of our imagination and challenge the very fabric of our understanding. We're about to dive into the mysterious and mind-bending world of quantum entanglement, a phenomenon that has puzzled and fascinated scientists for decades. In our journey through the mind-blowing world of quantum mechanics, we've encountered the uncertainty principle and wave-particle duality, shaking our understanding of reality's foundations. These principles have shown us that at the quantum level, particles can exist in multiple states at once, and their properties are not determined until they are observed. This has profound implications for our understanding of the universe, but hold on tight, because things are about to get even weirder as we delve into the enigmatic realm of quantum entanglement. This phenomenon suggests that particles can become entangled in such a way that the state of one particle is directly related to the state of another, no matter how far apart they are. This means that a change in one particle's state will instantaneously affect the state of the other, even if they are light years apart. Imagine two particles, born from a single event, intrinsically linked in a way that transcends distance. These particles are like cosmic twins, forever connected by an invisible thread. When one particle is measured, its twin instantly reflects the same measurement, regardless of the distance between them. This defies our classical understanding of how the universe works. No matter how far apart they are, whether separated by millimeters or galaxies, they remain connected. This connection is not limited by the speed of light, which is the ultimate speed limit in the universe. Instead, it operates instantaneously, suggesting that there is a deeper level of reality that we have yet to fully understand. This connection, my friends, is the essence of entanglement, a phenomenon so bizarre that even Einstein himself famously dubbed it spooky action at a distance. Einstein was deeply troubled by the implications of entanglement, as it seemed to violate the principles of locality and causality that are fundamental to our understanding of the universe. Despite his reservations, experiments have repeatedly confirmed the reality of entanglement. Entanglement implies a universe woven together in ways we're only beginning to comprehend. It suggests that the universe is not a collection of isolated objects, but a tapestry of interconnectedness, where everything is linked in a profound and mysterious way. This interconnectedness challenges our classical intuitions and opens up new possibilities for understanding the nature of reality. It suggests that the universe is not a collection of isolated objects, but a tapestry of interconnectedness, where the fate of one particle can instantaneously influence the fate of another, regardless of the vast cosmic gulf between them. This interconnectedness is not just a theoretical concept. It has been demonstrated in numerous experiments, providing compelling evidence for the reality of entanglement, where the fate of one particle can instantaneously influence the fate of another, regardless of the vast cosmic gulf between them. This phenomenon has profound implications for our understanding of the universe, as it suggests that the universe is a deeply interconnected system, where everything is linked in ways that we are only beginning to understand. This interconnectedness, this cosmic dance of particles, throws our classical intuitions about locality and independence for a loop. It challenges the very foundations of our understanding of the universe and suggests that there is a deeper level of reality that we have yet to fully comprehend. This cosmic dance of particles is not just a theoretical concept. It has been demonstrated in numerous experiments, providing compelling evidence for the reality of entanglement. In the next section, we'll dive deeper into the implications of this spooky action, exploring how it challenges our understanding of space and time. We'll look at how entanglement can be used to develop new technologies such as quantum computers and quantum communication systems that have the potential to revolutionize our world, exploring how it challenges our understanding of space and time. Entanglement suggests that space and time are not as rigid and unchanging as we once thought. Instead, they are flexible and dynamic, capable of being manipulated in ways that we are only beginning to understand. This has profound implications for our understanding of the universe and opens up new possibilities for exploring the nature of reality, and opens up new possibilities for communication and computation. Quantum computers, for example, use the principles of entanglement to perform calculations that are impossible for classical computers. This has the potential to revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Similarly, quantum communication systems use entanglement to transmit information in ways that are fundamentally secure and resistant to eavesdropping. Stay tuned, because the quantum rabbit hole goes deeper than we ever imagined. As we continue our journey into the world of quantum mechanics, we'll explore the many ways in which entanglement is reshaping our understanding of the universe and opening up new possibilities for technology and exploration. So buckle up, cosmic explorers, because the adventure is just beginning. All right, folks, buckle up, because we're diving into perhaps the most mind-bending concept in quantum mechanics, superposition. And to illustrate it, we're going to talk about a cat. Not just any cat, mind you, but Schrödinger's cat. Erwin Schrödinger, one of the pioneers of quantum theory, devised this famous thought experiment. Imagine a cat sealed inside a box with a contraption that has a 50% chance of releasing a lethal poison. Until we open the box, we don't know if the cat is alive or dead. Here's where it gets weird. According to quantum mechanics, until we make an observation, the cat exists in a superposition of states. It's both alive and dead simultaneously. Now, this isn't some kind of feline zombie situation. It means the cat's fate is described by a wave function that includes both possibilities. Only when we open the box, when we make an observation, does the wave function collapse, and the cat settles into one state or the other. This is the crux of quantum mechanics, where observation plays a crucial role in determining reality. For centuries, physicists envisioned the universe as a giant, perfectly predictable clockwork machine where every cog and wheel moved in harmony. Isaac Newton's laws of motion painted a picture of a deterministic universe where the future unfolded with unwavering certainty, like a well-rehearsed symphony. If you knew the initial conditions of all the particles in the universe, their positions and momenta, you could, in principle, calculate their entire future trajectories with absolute precision. It was a comforting thought, the idea that the universe was governed by order and predictability, a cosmic ballet of certainty. But then came quantum mechanics, and with it a profound paradigm shift that shook the foundations of classical physics. Quantum mechanics introduced an element of randomness into the heart of physics, challenging the very notion of a deterministic universe and bringing uncertainty to the forefront. It declared that at the fundamental level, the universe is not a predictable machine, but a cosmic casino, where chance and probability reign supreme, forever altering our understanding of reality. Quantum mechanics forces us to confront a universe that defies our expectations and challenges our understanding of reality. It's a universe where particles can be in two places at once, where information can travel instantaneously across vast distances, and where the very act of observation shapes the reality we observe. It's a universe that is both strange and unsettling, but also incredibly beautiful and awe-inspiring. As Richard Feynman said, nature's imagination is so much greater than man's. She's never going to let us relax. Thank you for joining us on this journey into the strange and unsettling world of quantum mechanics.